Okay, hi everyone. Uh, Before we start, is there any question about the previous session or sessions about the assignment whose deadline is very close, or about the midterm? Any ambiguity? No? Okay. So before we start, let me briefly talk about. So I made an announcement in CourseLink. It's time to form the teams for the course project, and also I have made a Dropbox folder in the course link for announcing the team members, as well as a brief proposal for your projects. Just for the proposals will not be graded. Just I want to know what you're gonna work on, and we are on the same page. That's the reasoning behind it. So let it be short. I think the number of paragraphs I said, maybe 3 paragraphs, and I have said what needs to be mentioned in the proposal. Currently we are 31 students. So we'll have 7 groups with 4 members and 1 group with 3 members. And yeah, feel free to discuss and talk to each other in order to find the people who have similar interests to you. And you can work either on theory or practice or a combination of both. And please let optimization be an important part of it, not just a very side part of it. And also feel free to discuss it with me if you need my discussion, my opinion on your project. I'll be happy to have discussion with you and talk about it. So feel free to approach me if you think you need some discussion about that. Also, and please upload your team members as well as your proposals before the deadline. Also, we have a midterm. Yeah, someone has asked a question in the chat. So, can be 5 members. I and 4 of my friends want to form a team. Is it possible, Michael? The thing is that, Alireza, if you want to do that, then one of the teams will be 2 members, and I think it's not a good idea to make it make a team 5 and the other teams. I'm thinking about the other teams. The other teams will not have enough members to include. So please let it be 4 at most. Even with that way, one of the teams will have 3 members. So it will be an issue, I guess. Is it okay? This is the situation. What can I do? Yeah, because the other teams will not have sufficient number of people. So that's one thing. If you have any follow-up, please let me know. Yeah, okay. Sorry about that again. And also about the Milad has said hi. Hi Milad? Is there any question? No? Okay, so feel free to ask me either by speech or in the chat. Also, another thing I wanted to tell you about the midterm. So about the midterm, by the way, next week we don't have a class because this is the next week will be reading week, winter break, and the week after that. So next week will be February 21st, because it's winter break or study reading week. Please correct me if I'm wrong. And the week after that, which is February 28th, we have the midterm exam. So the class session will be for the midterm exam. Please, everyone needs to be in the class time. So I expect 31 students to participate in the class time in that. Please, again, if you are even looking at the lectures offline, you need to be present in the class on February 28th. Every students, all 31 students need to be in the class time, please. If possible, highly suggested, please use a device which has camera, and please turn on your cameras. I trust you, please respect my trust and don't cheat. I'm sure you won't cheat. You are trustworthy and I respect you. So please also respect my trust. And you can use calculator and even I think I will make an announcement for that. Either bring a calculator which can, for example, invert a matrix or something like that. But if you don't have such calculators, that's fine. I have found an online website which can do that for you. So I will put the web link of that for you too. Therefore, whoever doesn't have a complex calculator, they can easily use that website. And I'm not picky, and I want even the exam to be joyful for you. So I won't make it too hard. It will be similar to the assignment as well as the examples which have been solved in the class. I think we have solved a lot of examples in the class time. And the material of the midterm will be until the end of the slide deck for KKT conditions. So a part of this session will be in the midterm, just a part of it. And I will let you know when it's done for the midterm. And also, so that's the thing. Yeah, and by the way, a good thing about the fact that we have the midterm exam during the class time is that if there is any ambiguity, feel free to ask, and everybody will hear my answer. So I will answer your questions. Anything, don't keep it to yourself. Exam is not like that. We can even discuss. So during the class time, during the exam time, so we can say, okay, there is ambiguity here. What should we do? So even if I give a hint, everybody will hear that. And at the start of the exam time or class time, I will upload the questions in the course link. You will download that. And also, so please bring these things. First, a calculator. Even if you don't have calculator, I will give you a link for calculating inverse of matrices and these things. Also, please bring ruler. Ruler is recommended, not mandatory, but for you to visualize for solving linear programming using visualization, I think ruler will help. Also, you need to have a paper and pen, and pen or pencil, whatever. And please write it in a way that we can understand, understandable. And also please have your phone or some device which you can take picture. It is also recommended, highly recommended that you, it's not mandatory, but recommended that you have a cam scanner installed on your device, so you can take, at the end, you can take picture from your response, and then you can use magic color in cam scanner. It will make it like it is scanned, and then you will upload the PDF. And I think the deadline of the exam will be during the class time, before the end of the class time. But depending on how the hardness of the questions, I'll decide on the duration, but I think it won't be more than the class time. And yeah, at the end, you will upload your solutions, and please try to have a stable internet connection. So this is the thing. Any question or ambiguity about the?
It's Eric here. I just had a question on, so just based on what I'm hearing, I assume that on CourseLink you'll post like something called, exam 1 or something. We'll open it and then we'll just work on it, during class time. We'll work through that test, and when we're done, we take pictures and hand it in. So it's essentially an assignment, but we have 3 hours to do the assignment.
Yeah, something like that. Yes, and also I'm here and for any questions to ask or any ambiguity. And I recommend that everybody also turns on just their camera. This is it's not mandatory, but highly recommended. Highly recommended that you guys. I know that maybe someone some devices don't have camera, but that's what I'm saying, that it's highly recommended that you use a device if possible that you use a device which has a camera and you can turn it on. And I trust you guys, and I'm not a picky person, so you don't need to worry about me. I'm not a picky person. I'm just trusting you guys.
Another question I have. So
Yeah.
what exactly, like when you say you have a camera, like what exactly are you looking for? So like, you know how in the first assignment we created like a Python that solves a problem. You're saying
Yeah.
like we wouldn't be allowed to use something like that.
What do you mean? I didn't get your point.
So like, for example, like in linear programming, like you can
Yes.
just create a program that solves almost any linear, like that just prints out a table. Is that
No,
what
there
you're
won't be
like?
any coding question. There won't be any coding
No,
question.
but I'm saying like what if somebody used that?
That's what I'm saying. I'm trusting you guys not to cheat.
So like
Yeah.
we're not supposed to be looking at our screen excessively, or is that kind of
No. I'm not. The only purpose of camera is just for a bit of uh, for it to be like a realistic exam. That's it. And
okay.
yes.
Okay.
Okay. Yeah. But yeah, and I think we're all adults, and you're trustworthy. I respect you, and please respect my trust. So that's the thing. And don't worry don't worry too much about the grades and these marks, because I think so far you have known me. I'm not a person who is very hard and picky and these things. The only purpose of this class is for you to enjoy the course. Someone has asked, is it open book? Honestly, I think it's not something which is hard to be open book or closed book, because if you learn how to solve linear programming and these things, I think uh, you don't need even the notes, because this is a procedure and you also know the things. So some formulas, what kind of formula did we have? But okay, let's make a poll. What's your opinion? I want your feedback. Would you like it? Would the class like it to be open book or closed book? Let's have a consensus on that. Yeah, please feel free.
I would say open book, just because number one, I don't think there's any way to control that. Like I think people might peek on their computer if they had some notes or something. But the other
Yeah,
thing is you kind of have to know the theory and how to do it. So if you don't know how to do, like dual simplex or something, you're not about to learn in that 3 hours. Like,
yeah, yeah.
so if it's open book and you don't know what you're doing, you won't do well anyways.
Yeah, yeah, I agree. So okay, so let's make it open book. But yeah, it doesn't mean that, because if we make it open, we are gonna make it open book. But please don't think that, okay, as it is open book, I don't learn or don't study, and I will study during the exam time. I think it won't be possible or feasible for you. So please study well before the exam. Yeah, but let it be open book. Okay. I will also make an announcement and mention all these details. But yeah, these were the things that needed to be discussed before the exam. Any other question or ambiguity? No? Okay, yeah. And again, don't be stressed about your marks and these things. I'm a kind of person, I want everyone enjoy the classes and the courses. So I'm not a person who make it stressful. So that's the thing. If there is no any question, let me start. So before we continue where we stopped, I wanted to let you know one thing which I kind of forgot to mention, in the interpretation of Lagrangian, do you remember I said you can see it as a regularized optimization where you are bringing the constraints close to next to the actual objective function, and that's kind of soft penalty that you're applying on the constraints. Constraints are kind of hard penalty. And I forgot to mention one thing. These dual variables, also known as Lagrange multipliers, these are kind of the weights of how we want to penalize, or how important this constraint is with respect to other constraints and the objective function. So assume the weight of the objective function is 1. You can consider these as weights. So weight of these constraints, so lambda I is the weight of yi(x), and nu I is the weight of hi(x). So these are weights for comparing the importance of the constraints with respect to each other and with respect to the actual objective function. And these weights are usually called, especially in machine learning, they are called regularization parameters, right? So for example, in optimization, you have some f of x, but you can have lambda, omega x, something like that. So where the objective variable is x, so this f of x is the cost or objective function, and this is the penalty or regularization term, and this is also called regularization term, and this is regularization parameter. And usually it's lambda is greater than or equal to 0. And even interestingly, we saw that the Lagrange variables need to be greater than or equal to 0. So similarity, you can see that you can see Lagrange variables or dual variables as the weight or regularization parameters for the relative importance of the constraints with respect to the other constraints and objective function. So that's one thing that I wanted to let you know. I forgot to mention that. Someone has asked in the chat, what will be the syllabus for midterm exam? Okay, I will answer that, and then we'll start where we stopped before. So the syllabus, yes, the syllabus will be until the end of the KKT conditions. So a part of this session. Yes, I will let you know when we reach that point. Okay, so now let me start where we stopped, and feel free to ask me a question if there's any ambiguity. Okay, here, so we talked about dual problem, dual function, also the gap between primal optimal and dual optimal, and the Slater's condition for a strong duality. Also, we talked about weak duality and these things. Now we are going to start with the KKT conditions. First off, we start with the stationary condition. We'll see what these are. So stationary condition. Consider this Lagrangian function, right? So if you recall that f of x was the objective function. These are for the inequality constraints, and these are for equality constraints. So as we discussed, Lagrangian function can be interpreted as a regularized cost function to be minimized, right? And therefore, we want to minimize the Lagrangian function rather than minimization of f of x with respect to the constraints y of x, yi(x), and hi(x). This was a primal optimization problem. But now let's minimize the Lagrangian, which is kind of a regularized optimization now. With respect to x, right? Because the optimization variable was x. But it has lambda and nu as also its variables because of those regularization parameters. Now we can find its minimum by setting taking derivative and set it to 0. Why? Because do you remember this is either discussed in your high school or in the calculus of the college or the first year of university. When we have a function, we want to find its extremum. Its extremum includes minimum and maximum. What do? And there is no constraint, right? So we take derivative and set it to 0. Hopefully, we'll have a closed form solution. If we have a closed form solution, we are done. If not, we need an iterative optimization. So this is also, I think some of you might have learned this in numerical analysis course. So we are taking derivative and set it to 0 because there is no constraint here in this optimization problem. And this means derivative of lambda with respect to x, another notation for that, right? Nabla x L. So this means take derivative, set it to 0. And for that, let's take derivative of this term here. If we do that, what is that? The derivative of the first term, f of x, derivative of f of x with respect to x. Derivative can pass through the summation, right? So we have, and this is also a scalar, so it comes out of the derivative. So it becomes lambda I, derivative of y of yix with respect to x. Because why? Because the optimization is with respect to x. So we are taking derivative with respect to x. And also here, derivative again goes through the summation. Also, this is a scalar, comes out of the derivative. We have derivative of hix with respect to x, and we set it to 0, right? So we have this equation here, 17. This equation is called stationary condition. And now you see it's completely makes sense because this shows the gradient. And why is it called a stationary condition? Because it shows that the gradient of Lagrangian with respect to x vanishes to 0, should vanish to 0. But vanishing to 0 means that it is equal to 0, right? And we just proved that in equation 17. And by the way, the reasoning behind the naming of a stationary condition is that a stationary point, do you remember, recall the preliminaries that we discussed. A stationary point of a function is a point where the derivative of function is 0. Where does it happen? Either on minimum or maximum or a saddle point. So a stationary point, recall this figure, here and here and here, and all these three, derivative is 0. So this is maximum, this is minimum, and this is saddle point. And minimum and maximum are also called extremum. So minimum, maximum, saddle points are stationary points. And in all of them, the derivative with respect to the variable is 0. That's why it's called a stationary condition. Okay, and this derivative holds for all dual variables. That's an important thing. So why? Because we took the derivative with respect to x. So we didn't take the derivative with respect to lambda yet, or nu. So it holds for all dual variables, and not just for the optimal dual variables. Not just for the optimal dual variables, but for all the dual variables. Clear so far? Okay.
Sorry. What does it mean? Like the derivative holds? Does it mean like the function, like the equation?
Derivative of what?
So like this derivative, like it says this derivative holds for all variables. Does that mean like the function holds?
You mean what? What does it mean to say derivative of f with respect to x? Do you mean that?
I know. Just your last sentence on this slide, like the derivative.
In this sentence?
Yeah.
Oh, what does it mean? It means that this equation 17, this holds, this is true for all nu I, lambda I, not just lambda I star and nu I star. Do you remember we had lambda I star, nu I star, where they maximize the dual function,
Oh,
G
okay.
of lambda and nu. And my point is that these are not just for lambda I star and nu I star. These are for all general lambda I and nu I. Of course, this equation is true for lambda I star and nu I star also as well. However, other lambda I and nu I also, if you put them in this equation, this is true.
Okay. Okay.
You get it? Okay.
Yeah. Thank you.
Yeah. Any other question? No. Okay. So complementary slackness, another KKT condition. So assume that the problem has a strong duality, right? So we have x star, lambda star, and nu star. X star minimizing the primal optimization problem, lambda star, and nu star. These are the vectors, so containing all lambda i's and all nu i's. And these are these maximize the dual optimization problem, right? According to equation 12, what was equation 12? Let's recall that. Let me go back. In most of the slides, whenever I'm referring to an equation, I bring it, but here there was no space. That's why I didn't bring it. So equation 12 is this. So we said that in a strong duality, G of lambda star nu star equals f of x star. There is no gap. Gap is 0 in a strong duality. So let's go back to where we were. So according to equation 12, we have this. I'm repeating it here. And equation 3 is this. Was this. If you go back and see equation 3, I'm repeating it here. And what was it? It says it's the definition of dual function. G of lambda and nu equals infimum or minimum of Lagrangian with respect to the x, right? And let's start from f of x star, equation 12. Here I'm putting it here. So based on that, f of x star equals G of lambda star and nu star. According to this equation 3, G of lambda star and nu star is infimum of, so here I'm repeating Lagrangian. So this term is Lagrangian, but I have lambda star and nu star rather than lambda and nu. Therefore, these are start, right? So this is Lagrange. This is Lagrangian of x, lambda star, nu star. Right? So far clear? Now, what do we have here? This is A. I have explained A here. Because x star is the primal optimal function for problem 1. So again, infimum is a linear operator. So we can say this term, infimum of these parentheses equals infimum of f of x plus sigma lambda I star infimum of yix with respect to x plus some nu I star infimum of hix with respect to x, right? That's why, and we know that infimum of those functions, the solution is the optimal primal variable. Therefore, I'm putting x star in these. So far clear? So because if you remember, we just discussing the stationary condition that it minimizes the Lagrangian. So we have these so far clear in step A. Now step B, I have explained it here. So what do we have here? Do you remember? Hix star is 0 because x star is an optimal primal variable, and optimal primal variable must be a feasible point, and the feasible point must satisfy the equality conditions, equality constraints, and the equality constraints are hix. So hix star is 0 because x star is a feasible point. So this term becomes 0, right? Now we have f of x star plus summation of lambda I star and yi x star. Okay, and also again, see, I have explained it here. We know that we already talked about it last session. Lambda I star is greater than or equal to 0. So the dual variable for inequality constraints in minimization is greater than or equal to 0 for the less than or equal to constraints. We already talked about it in equation 9. And also, as x star is an optimal point and needs to be a feasible point, it satisfies the inequality constraints. Therefore, all yi x stars are less than or equal to 0. So all of these terms, it's a summation, right? All of these terms are non-positive. Also, these are positive, non-negative. Therefore, the whole term, the whole summation is non-positive, less than or equal to 0. So it means that, so f of x star plus a negative or 0 term is less than or equal to f of x star. So we just proved what? What did we prove? Let's go back. So I'm repeating what we start. So we started with here. We started with f of x star and we came up with to this. Now I'm repeating it here. So we showed that f of x star equals this, and this is less than or equal to f of x star. We also showed that, do you remember I just discussed it. So as lambda I star is greater than or equal to 0 and yi x star is less than or equal to 0, the whole thing is less than or equal to 0 for all of them inequality constraints. So I'm repeating it here. So we have these two. And okay, so this means this term from one side is equal to f of x star, from one side is less than or equal to f of x star. In other words, it's sandwiched. It is sandwiched between f of x star and f of x star. Therefore, this term must be 0 because it is sandwiched between f of x star, and so it is equal to f of x star and less than f of x star. Therefore, this term must be 0. And according to equation 19, what was 19? Here, which I have repeated here. I have repeated here, right? According to this equation, so as we know that the summation is 0 and every term should be less than or equal to 0, it means that every term is 0. So for all I, which means for all I from 1 to M1 to M1 or M1, yes. For all inequality constraints, this holds. This is true. So we just proved that for all inequality constraints, the multiplication of lambda I star and yi x star is 0. And this is called complementary slackness. We just proved that. And notes that this is optimal dual variable for inequality constraints, and this is optimal x star is the optimal primal variable. So optimal primal variable, also optimal dual variable for inequality constraint. This and this is also inequality constraint where it has the primal optimal primal variable in it. So this multiplication is 0. And we just proved that. Any question? No? So I'm repeating it here. This is called complementary slackness. And it has a consequence. And what does it mean? So if, do you remember we said that lambda I star, in the last session, we proved that lambda I star is greater than or equal to 0. So it's either greater than, it means that either lambda I star is greater than 0 or lambda I star is 0, right? One of these two. So if it is greater than 0, according to this complementary slackness, yi x star needs to be 0, must be 0. In other, also we know that yi x star is less than or equal to 0. Why? Because x star is a feasible point and needs to satisfy the inequality constraints. And this also means either yi x star is 0 or yi x star is less than 0, right? Now, if yi x star is less than 0, according to the complementary slackness, lambda I star must be 0. In summary, here, So we have two cases for lambda I star. We have two cases for yi x star. This corresponds to this, and this corresponds to this. So whenever lambda I star is 0, yi x star is less than 0. It's strictly less than 0. Whenever lambda I star is strictly greater than 0, yi x star is 0. So in other words, if the dual optimal is non-zero, its inequality function of the primal optimal must be 0. If the inequality function of the primal optimal is non-zero, is less than 0, its dual optimal must be 0. Right? I'm just repeating these two equations here. Any questions so far? Everything clear? We just proved, right? Okay, now let's talk about KKT conditions. So in the previous slides, we derived, so do you remember primal feasibility and dual feasibility we discussed in the last session, end of last session. Stationary condition and complementary slackness, we just talked about it today. If you put all of these together, these are 4 conditions, and these 4 conditions are called KKT conditions, short for Karush-Kuhn-Tucker. And I will tell you the history behind Karush-Kuhn-Tucker in a few slides. So the primal optimal variable was x star, and dual optimal variables or lambda star, it's a vector, but you can put all of them together as a vector from lambda 1 star to lambda n1 star for all the inequality constraints, also nu star for all equality constraints. And so all of the primal optimal variables and the dual optimal variables must satisfy the KKT conditions. So this is a great thing in optimization. You know that whenever you solve some optimization problem, you must satisfy the KKT conditions. And sometimes you can use KKT conditions for solving the optimization problem, and that's called the method of Lagrange multipliers. We'll see it at the end of this slide deck. Okay. So KKT conditions or Karush-Kuhn-Tucker, we are summarizing them here. We are putting them all together. So a stationary condition, do you remember? It said that the derivative of Lagrangian with respect to x is 0. We are repeating it here. We showed that. Also primal feasibility. So primal feasibility means that the optimal solution, the optimal primal variable, which is x star, you know that it must be a feasible point. Otherwise, it shouldn't be an answer to the optimization problem. So it must be a feasible point. Therefore, it needs to satisfy the constraints because it's a feasible point by definition. So the feasible point should satisfy the inequality constraints as well as equality constraints for all of them, for all inequality and equality constraints. And this is called primal feasibility. Dual feasibility, we discussed in the last session that for inequality constraints, they should be non-negative for all of them. Or in the vector form, you can use the generalized inequality. So this means this. So all elements of lambda or all lambda i's are non-negative, either 0 or positive. And complementary slackness, we just proved that this, and it has also a consequence that we discussed for all the inequality constraints. As listed above, KKT conditions impose constraints on the optimal dual variables of inequality constraints. So you can see that these are mostly the constraints, especially these and these are working on the inequality constraints. This is also working on the equality constraint. So you can see all of them, we proved them, and it was very, now I think having them in one sheet all together makes sense. These are called KKT conditions. Also, we have some consequences of the KKT conditions in these slides that I'm going to talk about. So recall the dual problem, which we discussed in the last session. So maximization of the dual function subject to and dual feasibility. Remember, we said that all dual variables for inequality constants must be non-negative in the minimization. The constraint of this problem is already satisfied by the dual feasibility, right? The dual feasibility in KKT is exactly this constraint. Therefore, let's ignore that for now. Let's ignore the constraint of the dual problem because it's already satisfied must be satisfied in the KKT conditions. Therefore, this can be simplified to this optimization problem. We can have maximization of the dual function with respect to the dual variables lambda and nu. So we have equation 28 as this. And this gives us lambda star and nu star. Of course, lambda star must satisfy this dual feasibility in the KKT conditions. We can double check. After we find this lambda star and nu star, we can double check whether they are non-negative or not. Of course they are because they must satisfy the KKT conditions. And also we denote G of lambda star and nu star by G star, just to be shorter. Okay, and this optimization problem is an unconstrained optimization problem, right? Because the constraint, we assume that is satisfied by in the dual feasibility. And again, for solving that, we can take derivative, set it to 0, what we learned in high school. So let's take derivative of this dual function. And here now the variables are lambda and nu. Therefore, once we should take derivative with respect to lambda and set it to 0. And once we should take derivative with respect to nu and set it to 0, right? We can see it as a partial derivative because we have two variables, lambda and nu. Two sets of variables, actually. And now, so here, according to equation 6, what was equation 6? Let's recall that. What was that? Should go back. Equation 6. Okay, you remember this? G of lambda and nu is infimum or minimum of the Lagrangian with respect to x. And as it is minimized in the Lagrangian, we can say that it is Lagrangian of x star and lambda and nu because we are minimizing the Lagrangian. Do you remember? It is the minimization of the regularized problem rather than the problem itself satisfying the constraints. Therefore, we can say infimum of Lagrangian of x, lambda, and nu with respect to x is the Lagrangian of x star, lambda, and nu. And x star is the solution to this infimum of Lagrangian of x, lambda, and nu. The solution of this, or arg-inf or arg-min of this is x star, right? Now, according to this equation, remember this, let's go back to where we were. So G of lambda and nu is equals Lagrangian of x star, lambda, and nu. Let's go back. Okay. So according to this equation 6 that we just saw, I'm replacing this G of lambda and nu with Lagrangian of x star, lambda, and nu. We just saw the equation 6. And derivatives are put here again. So this is set it to 0 and this is set it to 0. Setting derivatives of Lagrangian with respect to the dual variables, here and here, always gives back the corresponding constraint in the primal optimization problem. This always is the case. So whenever you form the Lagrangian, we can see an example in a few slides. Whenever you take derivative of the from the Lagrangian with respect to the dual variables, it always gives you back the constraints. So this gives you back yix, and this gives you back hix, because nu were for the equality constraints, and lambda gives was for inequality constraints yix. So it means that it's kind of a verification because it gives you back, but it's kind of useless because you already knew that those constraints must be satisfied. And you'll see an example of how it gives you back that. So far clear? Okay. Equation 23, 29, and 30. So I think I'm repeating them here. So we had derivative of Lagrangian, set it to 0. This was stationary condition. Do you remember in KKT conditions? We also, in the previous slide, we just saw these two equations. Now let's put all of these three together and see that. So it means that derivative of Lagrangian with respect to x is 0. Derivative of Lagrangian with respect to lambda is 0, where lambda has x star in it. Derivative of lambda with x star with respect to the nu is also 0. So it says that the primal and dual residuals must be 0. By primal and dual residuals, we mean this, with derivative of Lagrangian with respect to primal and derivative of Lagrangian with respect to dual variables must be 0. Now, equations 3 and 28 can be summarized into the following max-min optimization problem. Let's recap what we had here. So do you remember equation optimization 28? We had maximize g of lambda and nu with respect to lambda and nu, and we called it the dual optimization problem. In the previous session, we defined that maximization of the dual optimization problem, dual optimization function. Maximization of the dual optimization function is called the dual optimization problem. So we have this supremum or maximum of g with respect to of lambda and nu, according to equation 3. Equation 3, I just showed you in a few minutes ago. This is the according to the definition. Equation 3 is the definition of dual optimization function. What was dual optimization function? G of lambda and nu is minimum or infimum of lambda Lagrangian with respect to x. That's why I'm replacing g of lambda and nu with the infimum or minimum of Lagrangian with respect to x. So as you see, this supremum comes from the dual optimization problem. This infimum comes from the definition of dual optimization function. Now, having them together, all together, so maximize the dual optimization function, which itself has an infimum in it. If you put them together, this also gives you Lagrangian of x star, lambda star, nu star. Why? Because this infimum gives you x star, and this supremum gives you lambda star, nu star. So all together, it will have Lagrangian of x star, lambda star, nu star. This is the optimal Lagrangian function value, right? And as you see here, we have max and min next to each other. These are very important optimization problems, especially in game theory. You have min max, either min max or max min. You can see this also as infimum supremum, or supremum infimum. Min-max problems or max-min problems are used a lot in optimization, especially in mathematics, of economy, and because in game theory and these things. Why? Because in game theory, what is game theory? Briefly, let me tell you. In game theory, you have several agents or several people or several whatever, several particles, several agents who are kind of competing with each other. They might be collaborative, or they might compete with each other. They might be aggressive, right? So if they are aggressive or they are against each other, one of them wants to have the profit, but the other one wants to decrease the profit of the other one. So one of them wants to maximize its profit, some Lagrangian, let Lagrangian here be the profit of one of them. But the other one is against that and wants to minimize that profit. The other one, the other way, there might be some cost for one of them. That agent wants to decrease the cost, the loss. The other one is against that and wants to maximize the cost of that agent. So they are competing with each other. You get this? That's why in economy, because in economy, usually agents want to compete with each other, like duopoly and these things. So when you have two, especially markets, which are against each other in the market, two companies against each other, we usually have a min-max or max-min optimization problem. And under some circumstances, min-max and max-min, under some circumstances, are equivalent. So when you have min-max, under some constraints, you have also max-min. This game theoretic optimization problem, max-min or min-max, is also used in GAN. If you have heard of generative adversarial networks, which were very interesting in artificial intelligence and machine learning recently, showed that you can generate some new images or some new samples from your data distribution, which are not necessarily existing. For example, they have used GAN for generating some facial images, and these facial images are not for existing people. So you see a face, an image of a face, but this person doesn't exist on the earth. And that's an interesting thing. For GAN is formulated using max-min or min-max optimization problem because it has a game theoretic approach. So you can see the dual optimization problem as a game theoretic approach, as a max-min optimization problem, right? Because you have the primal optimization problem, which wants to minimize that. On the other hand, you also have a dual optimization function which want to maximize that. Therefore, minimizing a bowl, also maximizing a bowl, you will have a max-min or min-max optimization problem, game theoretic approach. Any question so far? No? Okay.
No.
Great. Okay. So where KKT, some history of KKT conditions. Why do they call it KKT or Karush-Kuhn-Tucker? It's an interesting history. So in 1952, I have also put the papers in the references. So in 1952, two scientists named Kuhn and Tucker, they published an important paper. They proposed these four conditions that we just discussed. And however, later, so by the way, Kuhn and Tucker were from Europe. And at that time, it was a scientific competing. So between Europe and US. So US wanted to win the scientific match, and Europe also wanted to win that at that time. Therefore, when Kuhn and Tucker proposed that from Europe in 1952, people in US said, okay, someone went in US and found a master's thesis written by Karush in 1939, which was before 1952. And it was at the University of Chicago, Illinois. And I have also put the reference here. And they saw that, by the way, Karush, in his paper in his thesis, master's thesis, had already proposed those conditions, kind of, but it wasn't published as a paper. It was a master's thesis. No one had looked at that much. And they said, oh, by the way, in US, we had already proposed those conditions. So finally, they had a consensus. The scientific society had a consensus between US and Europe. They said, okay, Kuhn and Tucker didn't know about Karush's master's thesis, so it wasn't plagiarism. But let's name these conditions after all three of them. So it became Karush, Kuhn, Tucker conditions. So this was an interesting history behind these conditions. Now, and okay, here now we are gonna talk about method of Lagrange multipliers. Do you remember I said a few minutes ago, I said KKT conditions can be used kind of as validity check. You can check your answers. So when you can solve the optimization problem and then check your solution by KKT conditions, whether they are valid or not, they are correct answers or not. You can go the other way around. You can use the KKT conditions for finding the solution. Using the KKT conditions for finding the solution or solving the optimization problem is called method of Lagrange multipliers. Now we are going to talk about it. Okay. Consider this optimization problem 1, which we started from. Minimization of f of x subject to yix less than or equal to 0 for M1 inequality constraints, and we have M2 equality constraints. Now, let's solve this using duality and KKT conditions. This technique is called method of Lagrange multipliers. For this, we should do these steps. This is the procedure or the algorithm for that. So let's first write the Lagrangian as we discussed before. So what is the Lagrangian? We put the objective function. We also sum over the inequality constraints with dual variables lambda i's, and we sum over the equality constraints. And by the way, if your optimization problem was not in this format, you need to make it convert it to this form. We discussed in the previous session how to do that. So even if it is maximization, if you have greater than or equal to 0 constraints and all of these, or even when you have non-zero values, constants on the right-hand side of the constraints. For all of these cases, you can convert your optimization problem to this standard form, right? And then you write this Lagrangian in this way. You can also write it in this vector form. Now, what is the dual function? So do you remember we said, first off, we said that we want to minimize this optimization problem here. Now let's minimize the regularized optimization problem, which is the Lagrangian. So let's minimize the Lagrangian with respect to x, and let's call the argument the optimal objective variable for this optimization problem. Let's call it x dagger. This is called dagger, right? Like a cross. So x dagger, whatever. Just a naming, whatever you want to name it. Naming is not important, right? I call it x dagger. And here, so do you remember previously I said this means defined. In the literature, this also means a sign. Exactly like a sign in coding. When you are coding C, C++, Python, whatever. So when you say x equals 3, it means that assign 3 to x, right? So in optimization also you can write this as a sign. So based on the context, you can understand whether it means define. Usually in computer science papers, this means define, or it means assignment. You can see that. Hi. By the way, there is apparently a question here. Someone has asked, why don't we call it x star? Because Alireza, we'll see that. So Alireza has asked why you don't call it x star. Because we will find x star here in equation 36. We'll discuss that when we have lambda star and nu star in the Lagrangian. But kind of you can call that x star, but you will update x star in 36. You can see it in this way, but it doesn't matter. You eventually will find x star. But as lambda and nu are not optimal here, I'm calling it x dagger. All right. Okay. So I discussed this, and here it means that you can see it as a define or assign. Both work for here. So now this is an unconstrained optimization problem. Therefore, we can take derivative and set it to 0. Take derivative, set it to 0, as we had in high school or college. So now this in the previous slides, actually, as Ali Reza said, we called it X star. You can call it X star, but doesn't matter. Naming is not important for me. So G of lambda and nu equals Lagrangian of X dagger or X star and lambda and nu. Do you remember? This is the definition of dual function, because G of lambda and nu was infimum or minimum of Lagrangian of X lambda and nu with respect to X. According to the definition, we have this, question 33. Okay, now let's continue. Okay, we also said that in the dual optimization problem, we are maximizing the dual optimization function here. And let's call the argument of this optimization problem, or optimal arguments, lambda star and nu star, right? These are vectors. These have lambda i's, and these have nu i's. So we also have this. So at the third step, we do this. In the also now let's put these back into the G in order to have the G star, right? So in every optimization problem, we have the optimal objective function as well as optimal objective variables. So these are optimal objective variables for the dual optimization problem, and this is the optimal objective function for the dual optimization problem. In the fourth step, we have this. Now, again, let's go back to where we minimize the Lagrangian. But now we put lambda star and nu star in the Lagrangian. Now, when we do this, so we have only the argument will be X star. You can see it as an update in X star, whatever. So 36 is kind of similar to 32. Right, but it has lambda star and nu star in it. Again, it is an unconstrained problem. In order to solve equation 36, you take derivative of this term and set it to 0. Here, this is when you do that, X star will be a number or a vector, a constant vector. Why? Because it won't be based on lambda and nu anymore, because lambda star and nu star are values now. So when you take derivative with respect to the X, this term will be purely based on X because it doesn't have lambda and nu in it. Lambda and nu are already replaced by lambda star and nu star. And also it gives you X star. And now let's put it back into F to get F star. In other words, again, we are doing here the kind of primal optimization problem, regularized formats. And this X star is the optimal objective variable, and F star is the optimal objective function. So these are the steps. We'll have an example for that. So don't worry for understanding that. We'll have an example, but let's recap what we had. So the 4 steps, again, very fast. So when we have an optimization problem, step 1, we form the Lagrangian function. Step 2, we take derivative of the Lagrangian with respect to X, set it to 0. It gives us X dagger or X star. We put it back into the Lagrangian. So this function will be purely based on lambda and nu, because X is replaced by X dagger. So this also gives you the dual function, right? Now that you have dual function, we can solve the dual optimization problem, equation 34. So now it is an unconstrained problem. Take derivative with respect to the dual variables and set it to 0. It gives you lambda star and nu star. Put it back in the dual optimization, dual function. Put it back in the dual function. It gives you G star. So it gives you the optimal dual function, right? In step 4, now you have lambda star and nu star. Put it back in the Lagrangian. The Lagrangian will be purely based on X, because lambda and nu are replaced by lambda star and nu star. Take derivative with respect to X, set it to 0, because it is an unconstrained optimization problem. It gives you X star. Now put x star back in the primal function, which is f. It gives you f star. Finally, you wanted f star and x star. Yes, in this optimization problem, what did you want? You wanted x star and f of x star. This is exactly what we found here in equation 36 and 37. So this has solved our optimization problem. This procedure is called method of Lagrange multipliers. Any questions so far? Everything clear?
Yeah.
Okay, great. So as you see, we have used KKT conditions not for checking the optimal solution, but for deriving the optimal solution, for solving the optimization problem. Now, an example, a simple example. We have this optimization problem. Now it's not a linear programming anymore. It has a square in it, right? So it is kind of a more general optimization problem. Let's solve it. This is the first time in this course we're solving a non-linear optimization problem. We have two objective variables, and we have two inequality constraints. The inequality and equality constraints here are linear, but they don't need to be linear, right? Here they are linear. So these are the constraints. Here we have greater than or equal to. In order to make it a standard form, we need to multiply it by -1. So we have less than or equal to 0. Also, I have brought 1 to the other side of the inequality to have 0 at the right-hand side of the constraint. Also, we have this to make it standard. We bring 2 to the other side, so we have 0 at the right-hand side of the constraint. So this optimization problem has become converted to x1 and x2, x1 squared plus x2 squared plus 1, subject to x minus x1 minus x2 plus 1 less than or equal to 0, and x1 minus x2 minus 2 equals 0. By the way, we have here one inequality and one equality constraints. We might have several inequality and equality constraints in general. So here in this example, M1 and M2 equal 1. So let's form the Lagrangian. Here, this is the objective function. We have only one term for inequality constraints, so I call it lambda. But if we had two inequality constraints, we would have lambda 1 and lambda 2, right? Also here we have only one equality constraint, so I call it nu only. Is the dual variable, and this is the constraint. So this is a Lagrangian function. As you see, it's a function of x, lambda, and nu, and x has x1 and x2 in it. So it's a function of x1, x2, lambda, and nu. Let's take the what was the first step of the method of Lagrange multipliers? Take derivative of the Lagrangian with respect to x and set it to 0. Okay. Take derivative of Lagrangian with respect to x, and x is a vector. So the first element will be take derivative of Lagrangian with respect to x1, and the second element would be the derivative of Lagrangian with respect to x2. If you don't remember why, recall what we discussed in the preliminaries. Derivative of a scalar, because here output of Lagrangian is a scalar, right? Derivative of a scalar with respect to a vector is a vector. We have these two terms, set it to 0. So we have this system of equations. We can easily solve that. Just either use a Kramer method or these things, or simply here you don't need those methods. You can find x1, and also you can, from this you can find x1, from this you can find x2. If it was more complicated, we would find x1 based on x2 and put it in the other equation, so, and it would give you x2. So x1 dagger, or whatever you name it, x1 star is lambda minus nu over 2. So as you see here, yet x star or x dagger is a function of dual variables. because we haven't replaced lambda and nu with their optimal values, lambda star and nu star. Therefore, this x star or x dagger is still a function of the dual variables. Now, let's put back the x dagger in the Lagrangian. In this way, the Lagrangian will be purely based on x. The lambda and nu, sorry. It won't be purely based on lambda and nu. It will be purely based on lambda and nu, not x, because x dagger now is a function of lambda and nu itself. All right. When you put x dagger in the Lagrangian, your Lagrangian will be purely, as you see, based function of lambda and nu, the dual variables. Here I have just had some calculations, simplification of terms, and then you will have this, right? Okay, now the next step in the method of Lagrange multipliers, you don't even need to memorize that. I think the flow is obvious. Now you have this, so this is by definition if the dual function g of lambda and nu. As you see, it's a function of lambda and nu. I have put it, repeated it here. So this is the dual function. And now the next step is that we wanna, in the dual optimization problem, we wanna maximize the dual function. Therefore, we take derivative of the dual function with respect to the dual variables. And we have two dual variables here. We might have more of them, several, because we might have several constraints. But here we have two. So take derivative with respect to lambda and set it to 0. Take derivative with respect to nu and set it to 0. A system of equations. It gives you lambda star and nu star. All right? In here, it's so simple, but in general, it might be a system of equations where each equation has both lambda and nu. So you need to solve that. Okay, now we have found lambda star and nu star. As you see, these are numbers now. Let's put them back in the Lagrangian. Therefore, the Lagrangian will be purely a function of the primal variables x1 and x2. So these are just simplification of terms. Now we have that. We go back to where we started with. We said that we want to minimize the Lagrangian, which is a regularized format of the primal optimization problem. Therefore, we take, and as it is an unconstrained optimization problem, we take derivative of Lagrangian with respect to the primal variable x and set it to 0. Here again, we have two terms because it is a derivative of scalar with respect to a vector, x1 and x2. Set it to 0. Again, we have a system of equations. Here, the system is very simple. Otherwise, you might have equations. You need to find x1 based on x2, put it in the other equation, and solve that. So here it gives you x1 star and x2 star, right? You found your primal optimization variables, x1 and x2 star. Now you can put it back. So now here, these are the primal optimization variables, optimal primal variables. These are optimal dual variables. We found them one by one. We found them, all of them. So here in this slide, we found lambda star and nu star. In this star, we found x1 star and x2 star. We found all the optimal variables. What is f star? We can calculate f star and g star. F star is f of x star. And what was f? Look at the optimization problem which we started with. This was f, right? F of x as a vector, or it is f of x1 and x2, right? So we found x1 star and x2 star. Let's put them in the f and gives us 3.5. So this is the optimal objective function for the primal problem, f star. Now let's find the optimal objective function for the dual problem, which is G star. So G star is G of lambda star and nu star. And what was G of lambda star and nu star? Let's go back. Do you remember? Recall here. G of lambda and nu was this. So now let's put lambda star and nu star in this term. It gives us some value. So now I'm putting lambda star and nu star in this term. It gives me 3.5. Does it ring something in your mind? F star is 3.5. G star is 3.5. We know that for sure G star must be less than or equal to F star because this is a minimization problem, right? We are minimizing F, we are maximizing G, and we know that it's either we have weak duality or strong duality, right? So the gap is non-negative. G star must be less than or equal to F star. We discussed that in the last session. Here, in this case, interestingly, G star has become equal to F star, which is the definition of a strong duality. So we have a strong duality. But do you know why we have a strong duality? Can someone tell me why this optimization problem? Why this optimization
because
problem?
our basic was based on the strong duality.
What? Can you repeat?
Because we have X star, lambda star, nu star only when we want to at first start with these conditions.
No,
these
we might have an optimization problem which has, of course, some optimal x and lambda and nu, but it might have weak duality. So not necessarily whatever has a solution has G star equals F star. We might have G star less than F star, right? The reasoning is because of last session. This is the repeat of an example of a Slater's condition. In the last session, we had an example for the Slater's condition. Let me bring it. So refer to what we discussed in the last session, that the example here. Yeah, exactly. So in the last session, we said, okay, if we satisfy the Slater's condition, it means that we have a strong duality. We showed that, yes, this problem has strong duality. What did we do? We found a solution which satisfies the equality constraint, and the inequality constraint in it is strict form. So it satisfies the inequality constraint for less than 0, not less than or equal to 0, less than 0. This is a Slater's condition. And we showed that, yes, it satisfies the Slater's condition. So before solving this optimization problem, we knew that G star must equal F star here. And now we solved that using method of Lagrange multipliers. You might use other methods to solve that. But here we solved that using method of Lagrange multipliers, and we saw that, yes, as we expected by Slater's condition, strong duality holds for this problem, and F star is actually equal to G star. If you solve it, you had solved this optimization problem in this example, and G star was less than F star, then something must be wrong. Your solution might be wrong. If G star becomes greater than F star, it's absolutely wrong, because we either have weak duality or strong duality. In neither of them, G star is not greater than F star. If we know that it satisfies strong duality, then we know that they are equal. So this is the beauty of things. And now these are the references. So this is Slater's paper for Slater's condition in 1950, right? These are very historic papers. So this is Karush's thesis, master thesis in 1939, University of Chicago, Illinois. Department of Mathematics. And this is the paper of Kuhn and Tucker in 1951. They were not aware of Karush's thesis. And what is this? Oh, this is a historical discussion of Karush-Kuhn-Tucker, Kuhn-Tucker theorem. So you can look at this paper. And yeah, that's it. These are this is KKT conditions. Your midterm is up to this point. Yes. Any question before we start the break? No? Everything clear? Okay. So great. Let's come back at 8:35. Is that good?
Sounds good.
Okay, great. 8:35. I see. Thank you. So now let me share screen. Okay. We continue with first order optimization. A little bit change of gear right now. So now first order optimization. First, let's see the fundamental theorem of calculus, because we are going to use that in the derivation of gradient descent that we are going to introduce. Okay. There is a lemma, fundamental theorem of calculus for multivariate functions. I'm not going to bring the proof of this theorem. It's kind of out of the scope of this course, but we have a corollary of that, and we are going to prove that. So first, let's look at this fundamental theorem. It says that consider a differentiable function, which means that we can take derivative of that. It's smooth, and it's the domain is D. So and for any 2 points in this domain, X and Y, we can have this. So f of Y equals f of X. F of Y equals f of X plus this is gradient or derivative of f with respect to X transpose Y minus X. What does it mean? It is the inner product between derivative of f of X. Why? Because it's a vector. You remember f is a scalar, X is a vector. Therefore, derivative of f with respect to X is a vector. Y minus X is a vector too, because Y is a vector, X is a vector, Y minus X is a vector. So, and this is the inner product of these two vectors. We also have integral between 0 and 1. Let the variable of the integral be t, and t is here. So what does this mean? X plus t minus t times y minus x. The gradient of f of in this point minus gradient of f in the point of x. So when you have this becomes a vector. This is a vector. Again, this is also a vector. Again, this is the inner product between these two vectors. You integral over that, over t is between 0 and 1. It's very similar to what we had in definition of convex sets. Do you remember? We had alpha between 0 and 1. Similar to that here. So t is between 0 and 1. And you can see it as this term, you can see this term as small o of y minus x. Small o is in the complexity theory. So big O, small o. If you don't know, you can take a look at that. But it's an order. It means that this is a kind of a function, an order of complexity whose variable is y minus x. You can see it here. We have y minus x. We also have y minus x. So it depends on y minus x. So when we usually use small o when we want to approximate something, for example, we see that in Taylor approximation too. So it means that the rest of the terms is a function of y minus x. So it means that. So these two terms plus some rest of the terms as a function of y minus x. This is fundamental theorem of calculus, right? Okay, doesn't matter. Just something we are going to use. Now it has a corollary consequence. Consider a differentiable function f with domain D and let its gradient be L smooth. Recall L smooth Lipschitz continuity that we had in preliminaries. So now let's say that the function is the the gradient of function is L smooth, not the function. The function is not important here. The gradient of the function, derivative of function, needs to be L smooth. It means that, do you remember L smooth? It means that its slope shouldn't go too much higher than L. So this is exactly the definition of L smoothness for all x and y in the domain D. And for L smoothness, we had this. F of x minus f of y is less than or equal to L x minus y norm. However, now we are saying the gradient is L smooth. Therefore, f of x and f of y are replaced by gradient of f of x and gradient of f of y, okay? We are not talking about f itself here. And then says that if the gradient is L smooth, then for any 2 points x and y in the domain, we have this. It means f of y is less than or equal to f of x plus the inner product of gradient of f of x and y minus x plus L2 L half y minus x L2 norm squared. And as you see, it's very similar to the fundamental theorem of calculus. We are going to use that in order to prove this. You are going to see how we are going to use that in the gradient descent. So a proof of this, let's start with f of y. I'm repeating the fundamental theorem of calculus, which we showed in the last slide, based on equation 1 that we just saw. And now this term, I replace it with this term. So it means that the inner product of these two, I replace it with the multiplication of L2 norms. And this is the Cauchy-Schwarz inequality. We already discussed that in the preliminaries. We said that x transpose y is less than or equal to norm of x times norm of y. Now replace x and y with these two terms. This is like x, this is like y. You will have Cauchy-Schwarz inequality for these two terms. Therefore, we have less than or equal to, right? So far we know until now. Let's go to line 3. Line 3 is that, do you remember we said that let the gradient be L smooth. So we had this for any 2 points. Do you remember? Here we said let the gradient be L smooth for any 2 points. Now let the 2 points be x plus t, y minus x, and x. You will have this inequality that we are shown here when the 2 points are these two. Okay, now we can simplify this term inside the L2 norm and we'll come up with this. So in other words, we can replace this term with this with less than or equal to because of the L smoothness. This was the assumption of the corollary, right? We said that let the gradient be L smooth. Okay. Now, as L is a constant with respect to t, also the squared L2 norm of y minus x is constant with respect to t. They are not functions of t. They can be brought out of the integral. And we'll have integral of t dt from 0 to 1. This is equal to 1, right? Therefore, we have this. This is exactly f of y equals this term, and this is what we had in the corollary. It is less than or equal to because of this less than or equal to. So f of y is less than or equal to this term, which is the corollary. So we proved that. But we are going to use this corollary in the derivation of gradient descent. You'll see. Okay. Now let's start gradient descent. The first order optimization method. From now on, we are talking about iterative or numerical optimization. Numerical optimization or iterative optimization. What does it mean? It means that, do you remember, so when we have an optimization problem, minimize f of x, if it is unconstrained, we already have discussed it several times in this course. So when it is in unconstrained, it means that we want to find its extremum. Again, in high school or college, we learned that we can do this by taking derivative of x with respect to x and set it to 0. So this gives us, this is a function of x, right? And this gives us some terms based on x. So we can find x, if we can find x in a closed form, this gives us optimal value for x star. So this is done. However, sometimes it's very hard to bring x solely to the one side of the equation. When is that is the case, we can't have a closed form solution for x. For example, maybe the derivative is something like this: tangent of x plus 1 plus x2 over whatever, I don't know, sine squared x minus 3 equals 0. How can you find x in one side of equation? It's too hard to find x star. We can use numerical iterations in order to find the root of this equation, right? I think you have learned it in numerical analysis courses that you might have passed. So this is one way. Now, in such cases, we can use gradient descent. Consider this unconstrained optimization problem. For now, let it be unconstrained. So gradient descent is unconstrained. At the end of this lecture slide deck, we'll see how to deal with constraint optimization, constraint problems in first order optimization. But for now, let it be unconstrained. And we are assuming the general case where we can't find x star in a closed form solution. Therefore, we have to do iteratively. We have to find x star iteratively. And we have to move toward x star step by step iteratively. Gradient descent does that, and we see how. Okay, so gradient descent is one of the fundamental first order methods. Very fundamental. It was first suggested by Cauchy in 1874. You can see how old it is. And Hadamard in 1908. Very old, more than a century ago. So, and its convergence was later analyzed in reference 3, which you can see at the end of this slide deck. And consider this unconstrained optimization problem that we just discussed. Okay. In numerical optimization for unconstrained optimization, we start with some random feasible initial point. And this random point must be feasible, right? We shouldn't start with an infeasible point. We should be in the feasible set where here, as it is unconstrained problem, the feasibility set is only the domain of F. So wherever the F is defined is the feasibility set, as it is an unconstrained problem. But we should start with a random feasible point, and then iteratively we need to update it. Therefore, we can write it in this way. Let K be the iteration index. So for example, we start either with 0 or 1, whatever, 0, and then 1, iteration 2, iteration 3. And it means that x of, assuming we start with 0, it's x of 1. By the way, here it means a sign. We discussed here it means a sign. We can show it by arrow 2. x1 is x0 plus some step. x2 is x1 plus some step. And we continue until convergence. So this means this, right? And by the way, this step can be dependent on the iteration. So it can also be so like this, or it can be fixed. We'll discuss that, right? Okay, and we continue until we converge to sufficiently get close to the desired optimal point. We might not exactly reach that, but we need to sufficiently get close to that. Okay. Alirza has asked, is it explicit? You mean, what do you mean? Can you elaborate what you mean, Alirza? What do you mean by explicit here? Okay, I'll wait for you to either talk or chat and I will answer you. I didn't get your point. So you have said, okay, I will ask you later. Yeah, sure. So we have some step and we are doing it iteratively until we converge, sufficiently get close to the optimal point. Now, the step, we show it by delta x here. Sometimes it's also denoted by p in the literature. So p or delta x, as you see, this is a vector in general case. Why? When x is a vector, delta x also is a vector. When x is a scalar, delta x is also a scalar. In general case, even when sometimes x is a matrix, in that case, gradient is also a matrix rather than a vector. Then delta x will be a matrix too, right? So depending on what x is. Okay, now let's find the step size. So as we saw here, we have some in gradient descent, we have some step size. If you find the step size, the gradient descent algorithm is this, only this line. This is the gradient descent, right? And it is an iterative approach until convergence. Because by convergence, what do I mean by convergence? It means that, so whenever the distance, the difference of x1 and x2 is huge initially, but gradually, if the problem is not divergent, usually you get close and close to something. For example, x1 might be 2.3, x2 might go, if x is a scalar, assuming in this example x is a scalar, it becomes 1.5 something. Eventually, x, for example, 1000 becomes 1.0001, and x 1001 becomes 1.009, something like that, very close to the previous solution. As you see, the difference is getting closer and smaller and smaller. It means that the problem is convergent, not divergent. So we converge to some point, and if we continue, eventually we get very close to 1. So it means that x star is 1, right? So in this example. So now the only thing which is remained in gradient descent, as you see, it's very simple, is delta x. Let's find the step size. Now let's solve this. Let's see what's how to derive that. Okay, let the function f, which we are optimizing, here in this case we are minimizing, be differentiable, so we can take derivative, and let its gradient be L smooth. As you see, it rings something in your mind that it is assuming the same assumption in the corollary of fundamental theorem of calculus, right? Okay, so its gradient, let it be L smooth, not its slope shouldn't change a lot. It's gradient. It means that the second derivative should not be huge. When we say the slope of the gradient should be upper bounded by L, it means that the second derivative of the f should not be huge. Now, recall equation 3. What did we have in corollary of fundamental theorem of calculus? We had this. We just proved that a few minutes ago, right? Okay, now we say if we set x, so as you remember, we said this corollary was true for all points, any 2 points in the domain of x, right? We showed that. Let one of the points in the domain, one of the feasible points be xk, it means x in the iteration k, and let the other one be y, the other one be xk plus 1, which by definition of gradient descent is equals to xk plus delta x, right? Now let's put these 2 points in the corollary of the fundamental theorem of calculus, which I've written here. If we do that, we'll get this. We'll get this. Now let's bring this to the left-hand side. So we'll have this less than or equal to this term. Okay, so far clear? Okay. Until reaching the minimum, we want to decrease the cost function, of course, because the optimization problem was minimization of f of x. So we want to, in each step, we want to minimize or minimize the cost function or decrease the cost function in every iteration. Therefore, we desire that f of the next point minus f of this point be negative. It means that whatever I have at this point, in the next point, I want the function value be smaller. What does it mean? If I rearrange it, it means this, right? And I'm just replacing it by definition of gradient descent with f of x plus delta x. This is the desired thing in gradient descent, right? Okay, now consider this equation 6 that we just showed. We can say that as we want this to be negative, and this is exactly the left-hand side of equation 6, right? Inequality 6. So it means that the one way to achieve this, we might have other ways to, one way to achieve this is that we set this upper bound, because this is an upper bound for this term, right? We can set this upper bound to be negative. When the upper bound of this is negative, it itself is negative too. So one way to make this term negative is to make the upper bound of that negative. Now we have this. So far clear? Okay, I'm repeating it here. Now, therefore, what does it mean? It means that when we want this to be negative, let's minimize that. Let's minimize that with respect to delta x now. It's kind of a function itself, a function of delta x, right? We can see it as a function of delta x. Now let's minimize this function of f delta x with respect to delta x. Find some delta x which minimizes that, hopefully for this to become negative, because we want to minimize. So this we have that. Hopefully the solution of this will make this negative. We are considering the worst case scenario or the best case scenario. We are finding some delta x which minimizes that. Hopefully it becomes negative. Okay, this function, as you see, it's convex because this term is linear with respect to delta x, and this is quadratic. We know that even in your assignment, we showed that he showed that quadratic function is a convex function. Also, linear is convex function. So this function is convex with respect to delta x. Therefore we can, and this is an unconstrained optimization problem. So we can take derivative and set it to 0. And as it is convex, we know that the solution is neither maximum nor a saddle point because it's convex, right? It must be minimum. So when we let's take derivative with respect to delta x. So this is a linear term, therefore its derivative is this, and this is a quadratic form. So its derivative is 2. So L over 2 is a constant. We also have 2 times delta x. Why? Because recall that the squared L2 norm is delta x transpose delta x. It's a quadratic form. This 2 is because of derivative of quadratic. These 2 cancels, so we have L delta x. Now we set it to 0 because we want to find the minimum, right? And rearranging that gives us this. We found the step size. This is the step size, the optimal step size in the gradient descent. So now if we put it back in the definition of gradient descent, which was x of k plus 1 equals x of k plus delta x, we have this. So this is gradient descent. So far clear? Okay, I'm repeating this delta x here. Also, do you remember we showed this using the corollary of fundamental theorem of calculus. We showed it here. equation 6 here. We showed it here. Yeah, we have this. Now we have these two. Okay, let's consider these two together. This is here. I'm repeating it here. Let me think. Okay, now I'm substituting this delta x into this, or putting this delta x into this inequality, and I'm getting this. So here on the right hand side, I'm replacing these delta x with this, so I get this. Okay, and this, the left hand side is the same. The right hand side is this, where we have put this for delta x. So far clear? Okay. Now let's simplify the terms. How? Let's do that. Let's do that together. So this is a quadratic form. It's similar to x transpose x. We said this is a squared L2 norm of x. Therefore, I can write it as gradient of f of xk, a squared L2 norm here. Also, I'm repeating this term. Now, as this is a scalar, I can bring it out of the norm. We already discussed that in the preliminaries. And as we have a squared here, this becomes a squared. So squared 1 over L. And negative is also canceled because of the squared. So when we simplify these two terms, we can factor out squared L2 norm of gradients of f. We come up with this. And as you see, it is negative. So in other words, do you remember I said in this slide, let's minimize this term, hoping that this becomes negative. Therefore, this becomes negative. So we minimize this term with respect to delta x. So this upper bound becomes negative. Hence, this left-hand side becomes negative, which is desired in optimization. And we just showed that, verified that, yes, that's the case. The delta x that we found actually makes the upper bound negative and makes this function negative, right? Okay. So far, any question, ambiguity? Everything is clear? Do you follow? Can you give me a feedback? I want you to follow. Can you please give me feedback? Guys, can you please
I'm following along.
Okay, great. Okay. So please interrupt me if there is any ambiguity. So, okay, now we have found this step size in the gradient descent. So with this step, if we go, we can get close to the optimal solution. We can, however, there is a problem. This, can anyone tell me the problem without looking at this slide? So we found this step size, but there is a problem. What's the difficulty here? What's the difficulty in calculation of this step size? Can you guys please let me know? So what does this term has? It has L and gradient of f of xk. Gradient, we can take derivative, right? Yes, exactly. Arisa has said finding L. Finding L is hard. Do you remember one of you guys in preliminaries asked me, how should we calculate L? And I said, okay, we should take derivative, find the whole derivative for L on function f. We need to take derivative and find the largest norm of derivative, and then we say, okay, this is L, the lower bound on L, right? But that was for f, L smoothness of f. Now we have L smoothness of gradient. it means that we need to take the second derivative, and taking the second derivative is very hard. And we should do it for the whole domain and take the maximum, and that would be the lower bound on L. So finding L is hard. Let's replace it. Let's relax it. Let's make it simplified with some step. If we consider the whole thing, name it as a step, this can be named step size, eta, right? This negative is the same. This gradient is the same. The only thing which is I'm replacing 1 over L with some eta. And we know that eta should be positive because eta can't be negative because L is greater than or equal to 0, right? In definition of L, we have absolute value. So it's greater than or equal, greater than 0. It can't be also 0 because L can't be infinite here. So L should be positive. It's also called learning rate in data science and machine learning. Eta is either called step size or learning rate because you're learning something and it is a rate of learning. It kind of says how fast you want to converge to your optimal solution. If you set L to be a small value, then you move toward that optimal solution slowly, but more confidently. But if you jump faster, you are less confident, but you reach to that faster. Usually, especially in machine learning, you can have adaptive learning, where adaptive learning rates, where you start initially, you know that you assume that you are very far away from your optimal solution. So initially you have large step size, but gradually you decrease your step size. So this is adaptive learning rate. And we are going to see that. Okay. So if the optimization problem, so this now we have replaced, by the way, 1 over L with eta. Therefore, this is gradient descent, relaxed gradient descent, right? Where the step size is positive. If a step size is 0, it means that we never move from the initial point. Now we assume that it is a minimization problem, right? What if it is a maximization problem? Then the step size would, the step would be positive eta gradient of f rather than minus eta. Then the algorithm would be called gradient ascent rather than gradient descent. So why do we call it gradient descent? Because we are moving using gradients, by the way. In the step we have gradients, and we are moving in a descent direction of gradient because of this negative. We're kind of opposite direction of gradient. This is gradient descent. But in maximization, we are moving in the direction of gradient. So it's gradient ascent, right? Okay. Now, let's get back to equation 6 that we had. Recall equation 6. I'm repeating it here. Using equation 10 that we just showed, relaxed version of gradient descent, let's use this in equation 6. So let's use this in this. Put this in this. And what we'll have? This, I'm repeating left-hand side here. Okay, on the right-hand side, what do we have? Let me see. Okay. I'm actually putting this. I'm putting this here. Okay, it means that delta x we have here, we have delta x here. Let's replace these delta x's with this term, minus eta gradient of f of x k. If I do that, I will have this. Why? Because minus eta is a scalar, becomes out of the squared L2 norm, and it becomes a squared because of this squared. So we have eta squared here. And the remaining is remains in the L2 norm. Also here, so minus eta is because of this, minus eta in the delta x. We will have gradient of f of xk transpose gradient of xk. This is a quadratic form. I can write it as gradient of f of xk squared L2 norm, exactly as here. Right. Now I can simplify this term by factoring out gradient of f of xk L2 norm squared, factoring out this term, and I will have this. Okay, so I have this. Now I'm repeating it here. We found this. We just showed this, right? So it says that now in the relaxed version of gradient descent, let's see whether we can satisfy this desired thing or not. Whether can we decrease the function value at every step if we relax the gradient descent to have some step size eta rather than 1 over L. Okay. Now let's see. By the way, we know that this squared L2 normal gradient of f is greater than 0 because we know that it's always greater than or equal to 0, right? Because of the squared. But we know that it's greater than 0 if we don't have a stationary point, because in a stationary, why? Let me show you. When we have a convex function, until we reach to the optimal point, until convergence, we are never at the so in this point we have gradient of f equals 0, right, at the minimum. But until convergence, we are not yet there. Therefore, in all steps, we can assume that gradient of f, its norm, is greater than 0. But at the final point, we know that it's equals 0. However, if in our function we have some stationary point like this, maybe in the middle of way, the gradient becomes 0. So if we don't have a stationary point, if xk at that step is not a stationary point, we are sure that it's a squared L2 norm of gradient is greater than 0, right? We know that. So here, in this right-hand side, this is greater than 0. For this to be negative, because this was desired, right? For this to be negative, this needs to be negative. Because this term, we know eta is greater than or equal, greater than 0. We know that. This term is also greater than 0. Therefore, this needs to be negative. Must be. I'm repeating it here. This must be negative. Rearranging that, it gives some condition on eta. Oh my God. We started with gradient descent. It was dependent on L. In order to get rid of that, we said, let's relax it to some step size eta. Now step size eta has some condition based on L again. Eta is upper bounded by 2 over L. I think it's obvious because in the gradient descent we have L, therefore there must be some condition on eta in order to have this. Okay. So far clear? Yes?
Sorry, I have a question.
Yes.
For example, -5 is less than any positive values. For example, -5 is less than 2. And I think it can be positive too. Why should it be only negative?
Which part are you talking about? Sorry. In this slide, what are you talking about?
The element that you write it must be
yeah. Because
negative.
this do you agree that this is positive? Because we just said that here the step size must be positive. Why? Because eta, because 1 over L was replaced by eta, and L is also positive or non-negative, right? So eta must be positive. Eta shouldn't be 0 because otherwise we don't have any update in gradient descent. So eta should be positive. We know that eta is positive. This term is What happened? Sometimes this happens in my tablet. Just give me a sec. Okay, yeah, this term, eta should be positive. And this is, we just discussed that this is positive. Yes, when assuming that we are not at a stationary point. For this to be negative, shouldn't this be the whole thing be negative? And what was your counterexample? Can you tell me again?
No, it can be positive. For example, -5 is less than 2.
Oh, yes, but for this to always happen, we wanted this always happen. Because if you set this to 2, for example, the right-hand side, let it be 2. Okay, it might be 1. Then it means that then in the next step of gradient descent, we got worse. Right? We want this to always happen. We want this to always happen. For this to always happen, the right-hand side must be negative. Right? You get it?
Not completely.
For example, let the right-hand side be 2. Okay? Do you agree that in one of the iterations, maybe, we have this, we might have this, right? Is that clear? Because the right-hand side is 2. Yeah. So what does this mean? Let's rearrange it. Let me. So this is xk plus 1. So this means f of xk plus 1. It means that it got worse. In gradient descent, we want to get better at every step. But now we have increased the function value by 1. So I'm saying that at some iterations,
I got it.
Yeah, we want this always happen. That's why. Okay. Any other question? Okay. So recall equation 11 again. Where was equation 11? We found it in previous slide. Okay. I'm repeating it here. On the other hand, we can minimize this equation by setting its derivative with respect to eta to 0. Right? Now, again, this is an upper bound on this. So this is upper bound. We desire this to be negative. Therefore, one way to do that is that let the upper bound be negative. In order to do that, let's find the optimal eta which minimizes this value. Again, what we did for delta x, now let's do it for eta. Let's take derivative of this with respect to eta, and we'll have this. Yes, it's so obvious. Eta is a scalar here. Its derivative is very simple. Where we can factor out the squared L2 norm of gradient. Let's set it to 0. Eta will be 1 over L if we do that. Let's see if we... So 1 over L, by the way, is less than 2 over L. So it satisfies equation 12. Okay. Now, let's set eta to 1 over L in this equation 11. So I'm putting 1 over L in this right-hand side. It gives me this. Let's simplify it, factor out the squared L2 norm of gradient. We know that it's less than 0. Obviously, it should be because we showed here that eta should be less than 2 over L and 1 over L is less than 2 over L. Okay. So in other words, we are improving at every iteration. At every iteration, by minus 1 over 2L squared L2 norm of gradient of f, we are decreasing the function. Equation 40. So we showed that if we set eta to 1 over L, which satisfies less than 2 over L, we can have improvement in every iteration of gradient descent. Okay, Now we are repeating this. I'm saying you can make it even better. It can be not any value less than 1 over L, right? It would be a better improvement. But again, the lower eta, the lower step size, the later you reach to the optimal point. But you have more confidence. Okay, now we know that this satisfies this, so we have improvement. Okay, these are equations 13 that I'm repeating and 14. Equation 13 means that there should be an upper bound dependent on Lipschitz constant L on the step size. Therefore, we know that there's an upper bound. Hence, L is required. Again, L is required. And equation 14 shows that every iteration of gradient descent decreases the cost function. Exactly. That is what we wanted. And the amount of decrease is this. Also depends on L and depends on the gradient. So it depends on both gradient and L. That's why it's called gradient descent, because it's based on gradient. And why is it called first order method? Why is gradient descent a first order method? Because it uses the first order derivative. It doesn't use the second order derivative. It doesn't use Hessian. It only uses gradient, right? That's why it's called first order method. So first order optimization uses only first order derivative. Second order optimization uses second order derivative, and it might use first order derivative too, but it uses second order derivative, and which is harder to calculate. Now, okay, so as we saw, the gradient descent is iterative. So iteratively, it updates the solution. Therefore, if we start with iteration 0, then 1 and 2, so we have some points at every iteration, some optimal points at every iteration. Hopefully, they converge to X star, right? And we know that we are also decreasing the function. If the optimization is convex, we know that the solution is a global solution. It's either strongly convex or convex, and this might happen, right? When we have strong convexity, we have only one X star. But when we have this case where it's convex, but it's not a strongly convex, and this might happen, then we gradually come here, we reach this point. This is one of the X stars because we have a lot of X stars, right? Any of these minimize the function. The first that we reach, the algorithm stops, right? And by the way, if the function is not convex, for example, it's like this. This gradient descent will be stuck in the first local minimum that it finds, right? Here, it comes here, but it comes here. Depending on the step size. If the step size is big, it might miss some of the local minimums. For example, if the step size is big, it starts from here, but the step size is very big. It jumps here. It doesn't even see that. Then it can continue. So it might miss some of the local minimums depending on the step size, right? But we know that eventually we will find some local minimum. Either it is a convex function or no. If it is a convex, we are sure that whatever we find will globally minimize the function. If it's not convex necessarily, it means that we will find some local minimum, right? Local minimum is better than nothing. Let's find a local minimum. And even in many optimization problems, such as machine learning, usually local minimums are very good. Even especially, we'll discuss that. In neural networks, it can be proved that almost local minimums are very close and similar to the global minimum. So it's not saying that, I'm not saying that when you find some local minimum, it's bad. No. sometimes local minimums are the solution that you're looking for, right? You don't necessarily need to find a global minimum. So that's the thing. But we know that using gradient descent, we will find at least a local minimum. Hopefully this local minimum is good. Okay. Here I'm showing you, usually you can have plots of cost versus iteration, something like that. Cost is f value, right? So here, for example, you have f of x0, then f of x1, then f of x2, until you have f of x star. So here you have, these are x's, x0, x1, something like that. These are f of x0, f of x1, or something like that. And you expect that to be decreasing, right? Because we just showed that we wanna improve at every step or every iteration of the gradient descent. But we might have some oscillations. So if the objective function is convex, we see something like that. But if it's not convex, so here you can see a convex function, and we are of course improving at every step. We might at the end stagnate, but we are improving. But if it's not convex necessarily, it means that based on the step size, we might have some oscillations, but eventually we converge to something, almost. So we might have, for example, here, you can see in this example, in this step size, I'm jumping from here to here. So in this example, let this be like this. Yeah, I think this example is good enough. I don't need to draw another thing. So here, let this be, assuming that the step size you don't usually, because in gradient descent, you don't calculate the Lipschitz constant. You get some step size. You assume some step size and you move without eta, without a step size. Therefore, not necessarily in every step you improve the function. Sometimes you might go up and again down, up, down, something like that. So you might oscillate, but the global pattern usually is decreasing. So here, for example, you're moving to this point. Then with this step size, you're a bit increasing. Again, you're moving down. So, but the global pattern is decreasing. And when you have a lot of iterations, it squashes the plot in a way that you see the global pattern better. Usually this happens in neural networks. You will see a coding of neural networks soon. But when you have a lot of iterations, then you squash that. Then you will see the global pattern better. But you might have some oscillations because it means that your cost is not necessarily convex, right? Especially when it's highly nonlinear and highly non-convex. It means that sometimes cost functions are highly nonlinear, like this. Of course, you will have a lot of oscillations when you are doing gradient descent, right? But when you have convex function, it's very clean. Okay. Any question? No? Okay. Now line search. Guys, please ask me some questions. This also helps me rest a bit, because if I'm the sole speaker, I get tired also. I'm not sure whether everyone understood or not. Is there anything clear, or do we need any discussion or anything? Can you please let me know? It was clear. Yeah, okay. One good thing for me, if you talk, is that first off, I like it to be a discussion-based class. Also, I rest a bit because I'm a bit tired right now. But okay. If there is no question, I continue. Line search. Okay. We saw the step size of gradient descent requires knowledge of Lipschitz constants, right? L. And Also, we may not know the exact Lipschitz constant as we discussed. Hence, we can find the suitable step size eta by some search. Now we want to find some eta which is good, but without requiring Lipschitz constant. This search is called line search. Okay. Now let's see. These are the terminologies used in optimization. In line search of every optimization iteration, we start with eta equals 1. Because, do you remember, eta should be less than 1 over L. It means that eta, because L usually is a big number, L is usually less than 1. Because therefore, we can start with 1, and we know that the good eta is less than 1. And if it doesn't satisfy equation 7 with the step this was equation 7, if you don't remember. This was what we desired in gradient descent. We want to improve at every step of it, gradient descent, right? And this delta x is minus eta gradient of f. So I'm putting it here. We want this. We check this. So we check what we want. We desire this. We check what we desire with the eta that we chose. Let's start with eta equals 1. We are on a search. We are doing some search, right? With whatever eta we chose, let's check what we desire. Does it satisfy it? If yes, we are done. Our eta is good enough. It's not the optimal eta. It's good enough for improvement, right? But if it's not good enough, it means that if this eta doesn't improve the cost. So obvious, it means that, what does this mean? It means that f of next solution of gradient descent should be less than f of the previous solution of gradient descent, right? Every step we need to improve. If it satisfies with this eta, done. Not otherwise, let's halve it. Let's halve eta. We decrease eta by multiplying by half. So again, we do it. So do it iteratively until we are this is satisfied. Then we say eta is good enough. Let's do that. And then in the next iteration, we search again. For every iteration of gradient descent, we search for eta starting from 1, right? This is called line search. And the halving step size is repeated, as I said, until we have a decrease in the objective function. This decrease will happen. And when does it happen, by the way? When does this decrease happen? When we actually are satisfying what we found before in the previous slides. We said that eta should be less than 1 over L, right? We don't know L now, but we will halve it until this is satisfied, which means that this is satisfied. Whatever L we have, which we don't know, eta has become less than 1 over L. And this is the algorithm of gradient descent having line search in it. Let's see. So in gradient descent, we start with some random point, random feasible point, right? In the domain of f. So initialize it. We have some iterations. Just let it start from 0. It can start from 1, whatever. We initialize eta with 1. So in this, let me see. In this for loop, I'm doing line search. In this line 9, I'm doing a step of gradient descent, right? Just give me a sec. Yes, okay. I'm doing gradient descent. And what does it do? It says that, okay, By the way, we have a for loop in line 2 for gradient descent. These are the iterations of the gradient descent. We also have a for loop for the line search. So the line search itself has a loop, right? Because do you remember? We started with eta 1, we halve it until it improves the cost. It means that we also have a loop for the line search inside the loop of the gradient descent. In other words, in coding language, we have a nested loop, right? Okay, so we do check line search condition that we showed in the previous slide. If it is not satisfied, halve the step size. If it is satisfied, do one step of the gradient descent and then break the loop and go to the next iteration of the gradient descent, right? And by breaking the loop, I mean come out of this loop. So go to the next iteration of the gradient descent. But before going to the next iteration of the gradient descent, we might have reached the solution of the optimal solution. Check the convergence criterion. We'll discuss that. We'll discuss that in a few slides. So check the convergence criterion whether we have reached X star or not. If we have reached, it means that we are converged, and return X, the last solution. It means that you have reached X star. So this is the algorithm of gradient descent with line search, right? Any question? No?
No.
Clear? Okay. So that was simple line search. We have also a more complicated line search, or a better line search. And that's called Armijo line search. It's written as Armijo. Armijo line search, also called backtracking line search. So either called Armijo line search or backtracking line search. Armijo was a scientist in optimization. So it is a sophisticated line search, better method than the simple line search. And what does it do? Rather than equation 16, what was equation 16? The improvement, the simple improvement that we check whether the value of cost at the next step of gradient descent is less than the value of cost in the current or previous step of the gradient descent. Rather than that, so this is a simple line search, right? The simple check equation 16. We are adding to the right-hand side some term, which is this. By the way, P is delta X. Another name for delta X, doesn't matter, right? So it means that plus C is a constant, and it's a positive constant. It's between 0 and half. It's not 0, but between 0 and half. Also, P transpose means delta X transpose F of X. It means that the inner product of delta X, because delta X might be a vector, right? And F of X. So what does it mean? Let's see. By the way, the value of C, empirically they have seen that should be small. Empirically, experimentally, they have seen that it should be small, and it's usually 10 to the minus 4. You can see reference 5 for that. It's very small usually. And this condition, equation 17, is called the Armijo condition, or Armijo-Goldstein condition. These are scientists which have proposed this. And in gradient, so what, by the way, what does it mean? This is equation 17 is a harder or a harsher or more restrictive condition than the simple line search. It means that not only it should decrease the cost value, but more, it should be less than F plus something. So for example, if F is 6, simple line search says that I don't care if it is 5.9, it's good enough. Armijo's line search says no. Maybe it's 6. Assume that it is 3. Let me think. sorry, it's negative. Yeah, I was saying correctly. So it's because if you remember, P or delta X is a negative step. It's minus eta gradient of F. So it's -3. It means that in this example, if f of x is 6, simple line search says if it is 5.9, it's good enough. Go. But Armijo line search says no. In this example, if it becomes less than 6 minus 3, if it becomes 2.9, it's good enough. So it's a harder condition, right? It satisfies later than the simple line search. So it means that we need to search more in this inner for loop for finding better eta if we use Armijo line search. Now we know that P or delta X is this minus eta gradient of F. So if we put that in equation 17, we'll have this equation 18. It means that, again, this is a harsher or harder condition. We have other line search methods too. Another one is a Wolfe condition. Wolfe is also a scientist in optimization. For now, we don't introduce Wolfe condition, but we will see it later for when we are introducing second order methods, because especially in second order optimization, Wolfe line search conditions are used. But usually for first order, we can say, okay, line search or Armijo line search is enough, right? Okay. Any questions so far? No? Okay. Convergence criterion. For all numerical optimization methods, including gradient descent, there exists some convergence criterion, because we might never reach X star, right? It's very hard to reach X star. Sometimes we might oscillate close to X star. For example, if this is the function, based on our step size, we are coming down, 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 down. We reach here, maybe based on our step size, we go here, then we come back. So we are here, here, or here, or here. We never reach X star. Sometimes we can never reach X star because of a step size, if we are not decreasing X star. Assume that our step size is fixed. Or it's very hard, it's very time consuming to reach X star, especially when the step size is very small. Therefore, we say that whenever we say it's good enough, let's terminate the algorithm. That's the convergence criterion, right? Okay, there are several of them. One of them is when we have a small norm of gradients, because we know that the gradient is 0 or vanishes to 0 at the optimal point, right? We know that gradient of f x star equals 0 because of first order optimality condition. However, we say that whenever it becomes less than gradient, the norm of the gradient becomes less than epsilon, some small number, a small positive number, it's good enough. It means that we are close to the local optimum. Terminate the algorithm. The reason is the first order optimality condition, which is this. It means that the norm of the gradient at the optimal point vanishes to 0. It's 0, right? Where x star is the local optimum. Also, if the function is not convex, this criterion, there is a risk for this criterion. What is the risk? Without looking at this slide, can you tell me if the condition is norm of gradient of f of x, xk, if it is less than epsilon, let's terminate the algorithm. What is the risk? Someone has said in the convexity. Yeah, it's related to convexity. Assume that the function is not convex. What happens? Can you give me an example where we terminate the algorithm, but we are not at the solution?
Well, if it's at the if it's at like not the ultimate minimum, but like the local.
No, but yeah, but I said that if we reach the local, usually it's good enough. It's local because in gradient descent gives us at most a local optimum, right? If we are lucky based on the step size, we might find a better local optimum, but we eventually reach at the local optimum. So it's not the problem of gradient descent. We can't expect more than that from gradient descent. It gives us always a great local optimum. And this, if it is convex function, this local optimum is a global optimum too, right? However, yes, as Ali Reza has said, it might be saddle point. If it's not convex, in this point here, the gradient vanishes to 0, but it's a saddle point. It's not it's not a local optimum. It stops here. So this is the risk. Do you get it? So
yeah,
this
that
is
makes sense now.
Yeah, exactly. This is the risk of this criterion. Another criterion is small change of cost function. Because we are changing the cost, we are decreasing the cost function, right? But let's take the absolute value of difference of the cost functions. If we don't have enough change, it means that we are close to the, apparently we are close to the local optimum. If the absolute value is less than or equal to some epsilon. Let's stop that. Another thing is that a small change of gradient of function, rather than a small change of function, let's condition on the small change of gradient of function, because we know that the gradient is also changing, right, by moving that. And when we are close to the optimal point, the gradient hopefully becomes very close to 0. It means that, for example, it's 0.001, and the other one is 0.099, something like that. So it's very close, or 99, 98. We are getting close to 0. It means that we don't have enough change in gradient. Let's stop. Another thing is that we have maximum number of iterations. We can have, okay, we can say if we do 1 million of steps, then terminate the algorithm or whatever. Or we can have a combination of these conditions, criteria. For example, we can have a combination of this and this, or whatever. We can have a combination, intersection of these, whichever happens sooner, terminate the algorithm. I think we don't have enough time to continue, so until momentum we stop. Was it cool for you guys to learn gradient descent and first order, and also method of Lagrange multipliers? I think it was a cool session. Do you agree? What is your feedback?
Yeah, it was a good session.
Yeah, great. Yeah, thanks. So I think we learned a lot, and we will continue the session. By the way, next week we don't have a class because of the reading week. The week after next week, we have the midterm exam. Please tell your friends, whoever is not here, that everyone should be present in the midterm exam in the class time. So please, everyone, all the students need to be there in the class. Please let them know. And yeah, and some, as I said, but I think using them with Python will be hard. No, Alireza, it's not hard. As you see here in this, I assure you it's not hard. This is a nested loop. If you can implement this gradient descent in several lines of code. As you see, it's 13 lines of code. It's not very hard. And I promise you, if you try to get your hands dirty on that, you'll see it's very simple. It's very simple. Don't be afraid of these algorithms. When you understand why they work, I think their coding is very easy for you guys. Okay, so we'll continue in 3 weeks. So in next week is we don't have a class, and feel free to ask me questions if you have in chat. Also, the week after next week we have midterm exam, and in 3 weeks we continue with first order optimization. So in first order optimization, we continue with unconstrained optimization. At the end, we go to the constraint first order optimization. Then we go to second order optimization, Newton's method and quasi-Newton's method and these things, and also interior point method or barrier methods, which are used a lot in optimization toolboxes. And then we go to some meta-heuristic optimization, distributed optimization, and these things. Okay, great. So if there is no question, let's conclude the session. Any question? No?
Nope, all good.
Okay, great. So have a good night, and I hope you do great in your exam. Don't worry about that. The deadline for assignment is February 17th. Someone has asked 11:59. Yes, whatever we have mentioned in the course link, I don't remember it up on top of my mind. Please look at the deadline in the, you can see it in the course link as well as on the PDF of the assignment. Okay, thank you very much. Have a good night.
All right, thanks, Ben.
Thank you.
Bye.
Thank you. Bye.
Thank you.
Thank you. Thank you.
Sorry. So the midterm is in 2 weeks.
Yeah.
Right?
What?
Oh,
What did you say?
So the midterm is in 2 weeks time?
Yes, on February 28th. And please let your friends, everyone know that everyone needs to be present in the class.
Okay.
Okay, thank you very much. Thank you. Bye.
Yeah, bye.
Bye. Thank you. Good night.